right here to talk about my research about my one of the projects is like find new PET imaging probes for inflammation, in brain. So my technique uses this PET. So it's positron emission tomography. It's one of the biomedical imaging techniques. So I will briefly talk about what is PET, and then I will show an example about my recent publication about how to find a new probe for RPK1, which is a process in the neuroinflammation process. So here we show a image about the imaging techniques we discovered in the past more than 100 years. So we start with X-ray, basically around the 1900, and after that, we working on different approaches to find a new imaging modalities from X-ray, then go to the PET, ultrasound, MRI, CT, or we combine like different modalities together, like PET CT, PET MRI. So these are the top of this figure. Basically, they are for clinical use. And the bottom part in this figure is optical techniques, which for preclinical use, but also with the limitation of like clinical study. My focus is on the PET today. So there are advantages for each imaging technique. So for PET, we can do many things. For example, we can study the drug PK, by direct radiolabeling of molecules, either small molecules or peptide or protein. And next one, we can develop new imaging probes to see the target of interest, in the living subjects, either in animals or humans. The third one is we only inject the PET imaging probe in a nanogram scale, to human. So it's easy compared with other imaging agent to translate into the human if we need get approved by FDA for such study. So for the PET imaging, we have to inject some radioactive materials. People called imaging probe, imaging agent, PET ligand, or radio tracer, radio ligand. Many names, but they're the same, which is important and necessary for the PET scan. And we can do PET scan for in vivo measurement of target expression or function in the body. Basically, they start from the isotope production, for example, from cyclotron or other generators. And we go through some chemistry process to purify this ligand and do the formulation before we can inject to animals or humans, in the scanner, acquire images and do the further analysis. So regarding the application of the PET imaging, I would say there are two parts. One is like we can measure the protein or enzyme receptor density differences if you compare the patient with healthy control subject or within a disease model or a control model. So next one is we can measure the target engagement for drugs. Now, if we have the same target PET imaging probe with the drug, then we can see after certain time of injection, how much drug stay in the region of interest in the brain or in the other organs, for example, heart or spleen, whatever organs you want to see. That's can be used for like a guidance for drug dose selection or select a patient for clinical trial study. So how to prepare the radio tracer? For example, we always use some like short half-life radioisotopes for brain PET imaging. For example, the C11, F18, N13, O15. all of these isotopes with very short half-life. So that means we have to use a cyclotron on site to generate such isotopes, then prepare the radio tracer and do the imaging on the same place. It's very difficult to transport these tracers too far away. Especially for C11 and 13 or 15, we should do like in the same building. But F18, we can deliver to the same area. For example, I'm in Boston, so if I make tracer in my lab, so can ship to the Boston and has to be used in one day. So the cyclotron is a kind of generator for the radioisotopes. For example, the high energy proton beam from the cyclotron can react with the nitrogen in the air. And once they have the nuclear reaction, they can release this helium particle plus the C11. C11 is very unstable, so it's easily to react with the oxygen in the air and form this C11 carbon dioxide. Once we capture this CO2, C11 CO2, we can go to some chemistry reactions, convert the CO2 to different reactive moieties for chemical reaction. For example, the most commonly used carbon-11 resource is carbon-11 methyl iodide. Can be easily react with the nitrogen or oxygen group on these small molecules. So the reaction time should be very fast. So for C11, maximum time we put it like 5 or 6 minutes. For example, for this reaction, we use dimethyl with the methyl iodide and we heat at 100 degrees for 5 minutes. We get this small product. This is a tracer we get. We purify the tracer by HPLC and go through some formulation and pass the QC as required by the GMP lab. Then after that, we can inject to the human, for example, and we collect the signal from the human brain, and we in the PET scanner. So the whole process is kind of fast. For generate isotope, normally like 20 or 40 minutes, and the whole chemical reaction need like 40 to 60 minutes, and the scan maybe 1 to 2 hours. So that will be the whole scan day. And after that, the C11 tracer will be totally decayed. That means after the scan done, no radioactive material stay in the human body. No, it's all gone. So for the PET imaging tracers, there are basically 2 strategies we can use, like for different purposes. For example, we can have a tracer to measure the receptor or protein expression. So it's a kind of receptor based. For example, the dopamine receptors have many PET groups. So this is recopride. It's very commonly used D2 receptor imaging agent. And the second one is like we can measure the activity of the body. The most commonly used one is F18 FDG is the Hexy F18 labeled glucose, which measure the glucose metabolism related to the energy. So we can use it for many purposes. It's very commonly used the F18 tracer. And nowadays, like in a single hospital can do like hundreds of thousands scans each day. So it's very popular if you do the PET scan in the hospital. Also very useful for the research. So why we focus on to look for new PET ligand? So if you have a quick look on the FDA approved drugs, there are many targets available for drugs. But when we go back to the radio tracers, there are limited number of targets with such PET tracers can be used in human. For example, this is NIH summary with some human use radio tracers. This from a few years ago, so there are more targets available. So, but still not that many. Like here, like we say, less than 40 targets, only a few hundred or less than 200 molecules can be used in human. So that means if we compare the radio tracer and the drugs, it's so many targets is unavailable for such tracer. So we keep looking for the PET tracers for brain and for other organs, and for research and also for drug discovery. So how many FDA approved PET ligands so far? So here is a quick summary. So then the first one is FDG, or can be used for the tumor or heart or brain imaging. That's very popular tracer. And some Alzheimer tracers. There are 3 tracers to imaging amyloid in the brain approved by FDA. And one tracer, the bottom one, is for the tau pathology, also approved by FDA in 2 or 3 years ago. Our DOPA is like a dopamine receptor imaging agent, and some other simple small molecules for different cancer imaging, like prostate cancer imaging, and also some gallium-68 imaging agent, and also nitrogen ammonia or some like other inorganic tracers also approved by FDA. So far, there are about 13 PET tracers approved by FDA, and only like 100 to 200 go to the human. So we are still have a large space to find new tracers. So the example here I will tell is like neuroinflammation, and people know. So neuroinflammation is kind of an important target nowadays, especially when many drug trial failed for Alzheimer's. Many like big pharmaceutical companies and research labs move the directions from the traditional A-beta tau hypothesis to neuroinflammation and other strategies to look for new drugs for treat Alzheimer's or other disease. So I'm working on some targets related to the inflammation. For example, RIPK1. RIPK1 is for kind of key enzyme in necrosis, and also some NLRP3, which related to the inflammasome. So plus others. So the pipeline to have a PET imaging probe is is similar to find a drug at the very beginning. We need to start, as like confirming the target of interest. For example, RIPK1 in this case, and we need to design the lead compound. The lead compound can be from like screening or from the known publications, either from the research articles or patent. We need to find some lead chemical scaffold, which can be labeled with radioisotopes. Most of the time for the brain imaging, we use C11 or F18. So we need to develop the radio labeling strategy, based on these lead compounds. Then we go to the imaging evaluation, which is separate from the drug evaluation. Now, for the brain, the radio labeled compounds should have good penetration in the brain. So, for example, we do the rodent imaging. Also, we need to compare in the disease model. So, if we can see the difference, the in vivo imaging and the in vitro biochemical study should be matched very well. And then we can test in the larger animals, for example, non-human primate, such as this is a macaque image, to see the brain uptake before we can translate to the human imaging. And this is our goal for the PET imaging study. So if we have the new imaging techniques or imaging new chemical reaction methodologies, so that will help for the whole process to make it faster. Now, this is some like scanners of equipment in my center. So the automation radiochemical modules, and also some scanners, for example, the microPET CT, which for the rodent study, and the PET MRI for both like human or whole body, human scan. This some like scanners we could use, and also we're also working on some like new strategies for C11 and F18 radio labeling. So this some examples from like maybe 10 years ago, and recently we also keep working on the new strategies, especially for F18, to get more molecules labeling easily. Okay, so I worked on a C11 tracer called Martinez that many years ago, and actually before I joined the lab, the project already started in 2007. I continued this project from 2012 when I joined the lab. So basically, you see this pipelines similar as I showed in my last slides. Now we get like many compounds. Got the lead compound, and we get like maybe thousands of compounds prepared, and we compare the IC50, EC50 or PK data to identify some compound for radio labeling. Actually, we labeled more than 200 compounds from this lead compound with C11 or F18. So after radio labeling, and we evaluate in the animal models, the key parameters like brain uptake, PK, BioD, or specific binding are tox. Until we can reach to the FDA to apply the IND. So we apply EIND for tracer only. And it's approved in 2014, get IRB, and we started human imaging, and FDA approved paperwork. Okay, so if we want to find a target like RIPK1, so we need to figure out why we choose this target and why it's important. This is like a well-studied target, in past 10, 20 years, especially from Dr. Junying Yuan. She worked on apoptosis and found that RIPK1 was like a key kinase in this process, and also she worked on some like RIPK1 inhibitors. So when she did some research on disease, for example, Alzheimer's, they try to evaluate this expression of RIPK1 in the patient human postmortem tissues, as well as the AD disease models. So based on this figure, she published in PNAS. So we can see that in the AD patient, in figure B, the RIPK1 expression level is much, much higher than the controls. Also, the same thing in this AD model is APP-PS1 animal model. So we always see this increased level of RIPK1 in the brain. So with this traditional method, we can see the difference of RIPK1 expression between disease and controls. So our goal is to find a PET ligand can measure the same thing by in vivo in animals and human patients. So we start from the lead compound. Some examples here are RIPK1 inhibitors. For example, NEC1 and NEC1S from Dr. Junying Yuan. So this pretty early stage chemical scaffold. And later on, there are many other like NEC3, NEC4, NEC2. So also developed. Now it's the companies like Sanofi and Denali licensed these patents and working on clinical trials in different diseases like ALS or AD, phase 1 or phase 2. So compound 3 or 4 are GSK compound, different chemical scaffold also working on some clinical trials. So by checking these chemical structures, actually we labeled many compound. But the most promising one is NEC1S, which is showing here. So we can replace the chloride here to the fluorine and get F18 fluorine radio labeled to test its property as a PET ligand. So the chemistry is straightforward. Only like 2 steps we can make this compound we want. And also we need the compound for radio labeling we call precursor. Precursor means we have one place replaced by some reactive groups which can be used for radio labeling. For example, we can put this boronic acid ester here for F18 labeling. Now it also take like a few steps to make this compound 9. This is a precursor. Before we do labeling, we do some evaluation in vitro by some assays. We test this binding affinity or selectivity of our target compound. So in your assay, the kinase assay, including 468 target. Now, based on this screening, this most hit part is RIPK1, and some other target, for example, the PDPK1 and the SGK3 also has a minimum binding, so that will be an issue for the selectivity of this pattern ligand. Next one, we radio label this one, this compound. So actually, it's only one step reaction. For F18, if you remember, the half-life is like 100 minutes. Reaction time can be longer compared with the C11. The reaction takes 20 minutes and get good radiochemical yield, with good specific activity. And we inject the tracer to the animals. Now we test in the rodents first. Now we test baseline, which means inject tracer only, and blocking. That means pre-treat with unlabeled NY07 to see the decrease of signal to demonstrate its specific binding. So from the image and the curves, we can see the boron uptake is okay, and we can see the blue line here in the C. And after treatment, the radio tracer uptake is decreased. It's blocked by the unlabeled drug with a significant difference. So that means this tracer will be getting in the brain and also showing like specific binding. And we'll do some further analysis in different brain regions. So across the brain regions related to the AD, we can also see the same trend. So the baseline with higher uptake, and after the pre-treat, we can see the decrease of the signal. So that makes this tracer promising if we go back to this figure. So we are working on actually the monkey scans. So we have done some scans recently, and seems that the results good. So now we are working on the R&D paperwork, hoping we can translate this tracer to the human very soon. So, okay, this is my talk today, and thanks my lab member, collaborators, and my sponsors. Thank you very much, and glad to take questions. No, thank you.